I want to talk to you about the single most common physics problem on the AP Physics exam. And it's a separation of variables problem, and it's possibly my favorite physics problem. The reason it's my favorite problem is because it's got a submarine in it, and it's got calculus in it, and it's got drag force treated using calculus. So it's probably, for low velocities, it's actually an accurate calculation using just calculus, and we can get some real-world information about how submarines perform underwater at low velocities. For instance, when the submarine is sneaking through the water under silent running, it's turning its engines on at a very low and quiet speed because it's kind of trying to sneak and be quiet and stealthy. So it'll have a constant force from its engines, and because it's going at a slow velocity, it'll have a drag force pushing it forward, but at the same time it'll have drag force from the water pushing it backwards, and the drag force at low velocities is proportional to the velocity that the submarine is moving through the water. So the drag force is some constant based on cross-sectional area of the submarine, the shape of the submarine, that's why submarines are teardrop shape, and density of water and other things that you know for drag force. And at low velocities, the drag force is proportional to just v and not v squared. Incidentally, even underwater, the submarine will experience the force of gravity. And the force of gravity, however, is compensated by the buoyancy force because the water supports the submarine. And we call that buoyancy force Greek letter beta for buoyancy force, and that's inside the chapter that we skipped, chapter 15. Maybe at the end of the year we might have a chance to revisit chapter 15, but chapter 15 isn't on the AP exam, so for now we're going to ignore the buoyancy force and the gravitational force, because you can adjust the ballast tanks of the submarine so that the buoyancy force exactly cancels out the gravitational force. So our submarine problem just involves this constant forward force and making the submarine go faster, but notice the faster the submarine goes, the more drag force that occurs. Now, you might remember from chapter 6 that this kind of acts like gravitational force and air resistance, and so there's going to be a maximum speed with which the submarine can go when the drag force is exactly equal to the force from the engine pushing the submarine forward. So the question that this submarine problem asks is, what is the equation for velocity as a function of, or v of t equals what equation? So here's another reason why this is my favorite physics problem, is how do we solve this? Well, we use F net equals ma. And we write down just the forces on the submarine. So we have the constant forward force minus kv equals ma. And because it's a calculus problem, I'm going to write a as dv dt. So now we have F minus kv equals m dv dt, and notice now it doesn't have the a variable, it has only a v variable and technically a dt variable. Notice k is a constant, f is a constant, and m is a constant. So my only two variables are v and t, and so I've got a real shot at getting an equation for v of t out of this. And how I'm going to do it is I'm going to use separation of variables. And so remember, separation of variables, I get all my v's on one side of the equation and all my t's on the other side of the equation. And how you should think about it is this whole f minus kv part, that's the whole v term, and I want to get it all the way on the right side of the equation. So here's what it's going to look like if I make some room for it. I'm going to have f minus kv over here. This whole thing is the v part, and that's going to be on the right side. I put the m on the left side just because this is a harder integral and I want this cleaner. So the next thing I do is, in separation variables, I integrate both sides. And provided that my limits of integration match up, notice at t equals 0, v equals v naught. Remember, v naught is defined as the velocity at t equals 0. And at t equals some final time, v equals v final. And I could technically write v final here, but remember on page 21, regular v is v final, and v naught is v initial. So that's in keeping with our page 21 notation. But so these two integrals are still the same because these were the same, and when I separate variables, if I integrate both sides with matching limits, the equation is still true. So on the left side, I can factor out the 1 over m because the mass of the submarine is a constant. And then I can integrate dt, the integral of dt is in fact t, and I can evaluate the entire left side because I plug in t equals 0 and t equals t into this, and I have 1 over mt minus 1 over m times 0, which is 0. So I have the whole left side of the equation is 1 over mt. And so I've got here, I've got a little room here. This is what the integral looks like. I have on the left 1 over mt, and over here I still have to deal with this v integral. So looking at this v integral, I have to go from v equals v naught to v equals v final, and notice it's dv over a constant, and a v, and it looks like a 1 over x integral. And how we do it, if it looks like a 1 over x integral, we use u substitution. So I'm going to say u equals f minus kv because I want to make this look like 1 over x. And I'm going to have to change this v into a du for u substitution, so I differentiate both sides. Notice derivative of a constant is 0, derivative of minus kv, where v is a variable, just gives me minus k. And solving for dv, I've got minus 1 over k du, and so I'm going to put this here in for this dv up here. And then my integral looks like this. This is the dv, and then when I put in this minus 1 over k du in for dv, my integral looks like this. Now I want to get rid of this minus 1 over k, and here's what I'm going to do. Remember, I have the whole left side of the integral is 1 over mt, and I've got this minus 1 over k here, and so what I'm going to do is I'm going to multiply both sides by minus k and minus k here. So basically I've just taken this minus k that was on the bottom of a fraction and moved it over here because I can, because it's a constant, and I could factor out this constant and then multiply both sides by a constant. And the reason I do this is because now I have this nice clean 1 over u integral. So notice that integral of 1 over u du is a natural log of u. I still have my limits of integration from before. And here's what I had before. Natural log of 1 over u du. I'm going to plug in my limits of integration. And it turns out, remember I originally said u equals f minus kv, so I'm going to put that back into the natural log. And so my integral looks like natural logarithm of f minus kv, and now all I have to do is plug in my limits of integration. And I made some more room, so here I'm going to plug in my limits of integration, and I just plug in v, and I plug in v naught, and I subtract those two. Now you might remember from logarithms, if you have two logarithms that they're subtracted, it turns into a fraction. So it really looks like minus k over m, the logarithm of just one thing, because logarithm of this minus natural logarithm of this is the natural logarithm of that fraction. All right, so I want to solve for this v. All right, I want to get outside of the natural logarithm, and you might remember that to cancel out a natural logarithm, you raise it to the power of e. So that's called exponentiation. So I'm going to exponentiate both sides of this equation. So I'm going to raise both sides of this equation to the power of e, so e to the minus k over mt, e to the natural log of f minus k v over f minus kv. And you might remember this about e to the power of a natural log. Here I wrote more. Totally cancels out. E and natural log are completely opposite of each other. If you remember stuff about logarithms, this operation just totally cancels out a natural log. So here's what I am. E to the minus k over mt equals this. Remember, I'm still trying to solve for v. What the original problem is, what is the final velocity? What is the final velocity? And I'm looking for this v. I'm going to multiply both sides by this. So I've multiplied both sides by this, and I'm still looking for kv, and what I'm going to do is I'm going to move this plus kv to both sides, and then I'm going to move this to both sides, so I'm switching sides. But anyway, I've got kv equals this whole mess, and I'm going to divide, here I made some more room, and I'm going to divide through by k. So f over k, I did the fractions separately, and you'll see why in a minute. Because I can distribute this k inside of this parentheses, and I have e to the minus k over m, f over k, k over k, and that's going to cancel. So my final equation for v of t, notice this is v final, and my only variable is this t here. F and k, those are constants. V naught is a constant. That's the velocity of the submarine whenever it's very started at t equals 0 and it turned on its motor. Maybe it was coasting. Everything but this t is a constant. Remember, k has to do with the cross-sectional area of the submarine, the shape of the submarine, the density of the water surrounding the submarine. My only variable now is t. So I really do have a velocity as a function of time, and it looks like v of t equals f over k minus e to the minus k over mt times parentheses f over k minus v naught, because the k is canceled. All right, so this is ostensibly the equation for an actual submarine undergoing water resistance if you turn on the motors, the submarine motors, with a constant force F, and it has this equation. So that's what it ostensibly is, and so one thing we can do is we can use what's called extreme values to test it. And by extreme values, I mean t equals 0 at the very beginning, for instance, and then later on, after a long time, t equals infinity. So to start with, t equals 0, I plug in 0. That's pretty obvious. So 0 for t, I've got the same equation, and I have e to the minus k over m times 0. That's going to be e to the 0 power. E to the 0 power is just 1, and so I have this e to the 0 power just turns into 1, so it's just a 1 in here. And notice I distribute the minus sign after making a little room, so I've got minus f over k plus v naught. Those two f over k's cancel. And I got, amazingly, at t equals 0, v equals v naught, the original speed of the submarine that I was given at the beginning of the problem. Remember, the submarine was originally going at some initial speed v naught at t equals 0, and this equation amazingly said at t equals 0, it gives me v naught. Isn't that satisfying? After all that calculus, the initial velocity is in fact v naught. So I've got the same equation, and the other extreme value is what is the speed after a long time? So, and by after a long time, in physics, a long time means t equals infinity, so I plug in infinity for t, and notice you might see this coming, e to the minus k over m times is e to the minus infinity. E to the minus infinity, if you don't know, is going to be 0. This whole thing is 0. So we've got the velocity of an infinite time later is not infinity, it is in fact a constant f over k. Now let's look at our original problem. Remember, in our original problem, we turn on our motors the motor turns on, it's going at the initial velocity. Drag force, the faster the submarine goes, the more drag force is, and if you think about this, eventually it'll go so fast that the drag force exactly cancels out the motor force, and that's called its terminal velocity. Just like a skydiver falling through the air, eventually the wind resistance exactly cancels out the gravity pulling the skydiver downwards and accelerating them. So when the submarine reaches its maximum terminal velocity, the acceleration is 0. And notice that velocity, if I solve for the terminal velocity, is in fact F over K for my original equation. So notice that even from the original equation, when we very first started, we could have guessed what the final velocity of the submarine at the very beginning was. It's going to be F over K if you wait for a long time. You turn on a submarine motor with constant force. Eventually, the water resistance will bring it to a maximum speed, and the only way you go faster is to turn on the engine more. But this, in fact, simple calculation for what's the maximum velocity agrees with our v of t equation. So that's also very satisfying. After all that calculus, we have fairly good confidence that that equation really is, just using calculus, knowing something about drag, we can actually get the velocity versus time equation for a submarine. Now, using these extreme value ideas, we can get a pretty good idea of what the graph in fact looks like. So let's say the end of the problem is what does in fact the graph look like, and we know that at t equals 0 here, it starts out at v naught. So at t equals 0, it starts out at v naught, and then after a long time, it's going to end up after a long time with some maximum possible velocity. That maximum possible velocity is f over k. So it starts up and it gets to this f over k with an e to the minus t. So it's going to be an asymptotic approach because of the e to the minus t. So we can reasonably assume that the graph is looking like this with this e to the minus t form. In fact, our velocity versus time equation is true. And what I'd like is the best thing about this is it is kind of a lot of algebra and a lot of calculus, but it's actually a true equation for the performance of a submarine at low velocities, including the drag on a submarine, and we have an actual equation for this. Now notice if you wanted to find the acceleration, you would just take the derivative of this. That's not so bad, taking the derivative of this. You could, if you wanted to, also calculate the position versus time equation by taking the integral of this. It's a kind of a long and tedious integral. Usually that part's not given in an assignment, but it's possible. You yourself are already good enough if you wanted to spend the 20 minutes or so it will take you to take this integral. Well, actually, probably not 20 minutes. But you could do it if you wanted to. But this is kind of a famous problem, and I think people who write the AP exam love this problem because it has drag in it, it has calculus in it. In fact, this is the only reason why there is U substitution on the AP physics exam, is so you could have a shot at doing this problem, because it does. That's how important, that's how much we as physics teachers like this problem. 1, it's about submarines. 2, it involves calculus. And 3, it gives this real result. If you turned on a submarine at constant force, it would perform like this until it reaches maximum velocity. And to go any faster, you'd have to turn up the engine power. Right? Isn't that a wonderful, wonderful physics problem? And that's what I'm going to leave with you. And really what this is, it's the power of calculus. Now remember, calculus is just math. It's just about concepts. But with only a little bit of physics, we can use math to really tell us something about how the actual world works, how submarines actually perform underwater at low velocities in silent running conditions, for instance. Now I will tell you that if you turn up the motor enough, the velocity isn't going to be proportional to minus kV. It'll be proportional to minus the drag will be proportional to minus kV squared. So there's a small domain where this applies, but nevertheless, I feel like it's where calculus says something true about the world. And isn't that a lovely problem? And the last thing I want you to leave with is, submarines were in World War II called U-boats for underwater boats, so they were called U-boats. And my personal opinion is that this is why U substitution is called U substitution, because it's really referring to the U sub. Get it? Get it? U substitution. It only works for submarines, or that's why it's invented maybe. U sub, because it's a U-boat and it's a submarine. That's why it's called U sub, because you use it for U-boats. I'm so funny.